So where were we? So I think I have to finish the proof, no? So we developed quite a bit, and now it's time to finish the proof. So let's see which are all the tools we got. So we have this suspension space. We have the Lyapunov exponents chi I with this kernel of chi I. We have the spaces AI, and more important, the manifolds Wi, which here are all one-dimensional. We have our measure mu bar, which comes from the measure mu on M. And we have the decompositions mu hat I P on Wi and mu bar I P on EI. The space is EI. I goes down. I goes down. And we had these identifications HIP from EI into WI of P, which satisfied the most important property here with all these objects are, well, that these are the conditional measures. Mu bar is ergodic. That's the only thing that we care here. Ergodic for alpha. Then we have that if Q belongs to WIP, then the change of coordinates is a translation always, just to emphasize, 0 is going to P. The second was, which in a sense was already used, but it worth probably saying it again, that when I see in coordinates, when I look this guy in coordinate, oops, the -1 I guess should be here, not here. So I go from here by Q and then come with the P. So when I see the dynamics in coordinate, it's just multiplication by this number. The third comes in two statements at the same time. One is that if Q belongs to, well, there is a set of full measures, because these guys are only defined on sets of full measures. So there exists R containing an alpha mu bar of R equals to 1, such that if P or Q belongs to Wi of P intersected with R, then mu hat I P is equal up to a number to mu I Q. So these measures coincide. And using the fact that these two measures are related by HIP, and then mu bar IP is equal by definition mu hat IP, and this is actually the definition of this object and not of this object, but still we define it this way. Then using this fact plus the first fact plus this property here, we get that this translation TPQ star mu hat mu bar IP is proportional to mu bar IQ. And I guess this is bringing the Q to the P, and so this should be, I guess, the other way around. But one is a translation of the other. Okay. 4 is just the very definition of conditional measures, which is that the mu hat I p of the complement of R is 0 for every p in R. So the conditional measures are fully supported on R. Now I need a last definition. Let's see what else we may need. Oh, I think I made, oh, there is the dynamics statement 5 before we go to the entropy property. So if we call this Ls of B, so it's multiplication by e to the chi is, maybe we just increase. Let's just call it S. V is this multiplication. Then we have that for every P in R, or for every S, and S in R2 and P in R, such that alpha S of P also belongs to R. And I keep on, I could assume R is alpha S invariant for every S, but this amounts discussing even more ergodic theory, which I don't want. If I had only countably many S to discuss, then it's a triviality because I can do the intersection of all of them. Since there are uncountably many S, then I should really work harder, which I don't want to do it. When it comes to the game, I will only play with countably many S, so this is not really a strong requirement. So then I have L star of mu pi is proportional to mu bar I alpha S of P. And this follows from the alpha S invariance of the mu bar. Then the sixth property, which is what we spent quite a bit last time to discuss, which is pi partition trick. It says that for every continuous phi, there exists a set of full measure. Actually, I can state the way I want it, which is for every L1 phi, there exists a set R phi of full measure which is the set of guys where Birkhoff ergodic averages exist for this phi, essentially, for every S. Oh, I forgot to take S naught in X kernel of. So take here S naught in the kernel of chi I. So this also depends on S naught. Again, I could make it independent of S0, but I don't want to make it independent of S0. I don't need to do it. So I have this set of measures such that if P belongs to this guy and Q belongs to this guy, and I actually can assume this guy is inside the previous R, then phi tilde of P equals to phi tilde of Q, where phi tilde of X is 1 over limit 1 over n sum from 0 to n minus 1 of phi on alpha k s naught of X. Okay, so by Birkhoff this limit exists, and we know it's constant along orbits, and this is telling us that it's constant along the Wi foliation. That was all the shop last time. And actually, if I want to happen for countably many phis, I can still do it by intersecting this set. I think I will, depending on how I do it, I can do it for 1, 2, or maybe countably. Okay, now corollary of all these properties. Maybe first let's define GIP is all the translations T from EI to EI translations such that T star mu bar IP is proportional to mu bar IP. Okay, so I have this group naturally, and condition 3 is a guy producing elements there. Well, condition 3 is not yet, because I want the P go to the same P. So I need some extra property. I have to put in a sense condition 3 and condition 5 to do that. But anyway, so this is first lemma. Says two things. One, GIP is a closed subgroup. This requires a proof. If I put an equality here, it would be really a triviality, but I'm not putting an equality there, so it really requires some proof, because the constant could be exploding, and then you have to be careful. I didn't said it, but these are all radon measures. Which means they are finite on compact sets. Okay, so that's, let's prove just this lemma, that this GIP is a closed group. So we take Tn going to T, Tn in GIP. So Tn of B is V plus some T sub n for every n, and T sub n is going to T. So that's our assumption. And we have this constant Cn, C sub n, such that T star mu bar IP is equal to C n star mu bar IP. So that's the definition of this thing. And now we have a reasonable useful statement, which is that this is an equality among measures. So we get that Cn, okay, I needed one more term that we discussed last time, and I wanted to discuss it again. So let's put here 7, even though it should be 0, which is P belongs to the support of, or P belongs to the support of mu hat IP, and 0 belongs to support of mu bar IP for every P in R. So Cn is mu bar I P of the interval minus Tn, which is a translation, sorry, not minus Tn, Tn 1 minus 1 minus Tn 1 minus Tn divided by mu by IP of minus 1, 1. Okay, and I'm dividing by something which is not 0. That's why I assume this condition 7. That tells me that this number is positive. So I'm happy. This Tn is going to T, which implies that for n large enough, Cn is smaller than or equal mu bar IP of minus 1 minus 2t 1 minus 2t, I guess, or maybe I have to put plus 2t. Let's put absolute values here. Really doesn't matter. Some interval which contains all these guys simultaneously divided by mu bar. And this is just a number. So this measure could have atoms, so I cannot really claim that as Tn goes to T, these values converge to the limiting value, but you have the semi-continuity coming from here. So Cn is bounded, so I can take Cni, the subsequence going to a limit. I can forget about the sequence, only go to the subsequence, because the only thing I have to show is that T preserves this measure up to a multiple. So I just can forget about the subsequence and go back to the sequence and assume the sequence is Cn is going to C. And now that I have the conversions of the numbers, there is not much more to do. Okay, because I have that E phi from Ei to R is continuous, and the conversions here, I don't care about conversions, so I will talk about conversion is continuous with compact support. I don't know why I'm taking this guy, but I'm not sure I really need to use this guy, but anyway, let's do it. The integral of phi d mu bar IP over Ei is equal to, by the definition of the Ci's of the Cn going there, which are all positive. Okay, where is Cn? Let's put them in this side then. This is equal to the integral of phi compose Tn Duma for Ei. Since Tn is converging to T and phi is supported on a compact set, then I have that this is converging to the integral of phi. So these conversions I have. And since Cn is going to C, this is going to C phi p. So I get that this is equal to this for every continuous compactly supported function, and hence this implies that E star mu bar IP equals to C. And then I know.
So you see the constant generated by the push forward of T?
And C, as an outcome, the C will happen the same as with the Cn. So you will get that mu bar IP of -1 minus T, 1 plus T, 1 minus T, divided by mu bar IP of -1, 1 is equal to C. Just because it's true for every guy, in particular for this. Okay. So we get that this is closed subgroup. So far we are not getting anyone inside there, so it could be discrete and even trivial always. So we have to do something so that it is not trivial. So what we are going to do is to show next lemma, which is essentially putting together 6, 5, and 2, and 3, sorry, and 4. It's essentially putting everyone together, which says that if we call O of P equals to GIP of 0, which is the orbit of 0, so these are P of 0 such that P belongs to GIP. So it's the orbit of by this subgroup, which is what you do by identifying the translations with the subgroup of EIs, essentially. We get that mu bar IP of the complement of this guy is 0. So the measure is supported there. Okay, so let me prove it here. Proof. So if what we're going to show is okay, I want a different formulation of 6, which is more to the point we have, which is 6 prime, which says that if Y is a Lebesgue space, so it's Borelian equivalent to the interval 0, 1 plus countable many point, and psi goes from M alpha into Y is such that psi composed alpha S naught is equals to psi for almost every point, for mu bar almost every p. Then there exists a set R psi S naught such that, and essentially the same conclusion holds, but with psi, such that if Q, if P belongs to this set, and actually I can assume this inside of the previous R, and Q is in WIP intersected is not, then psi of P equals to psi of Q. And the proof is really a triviality because I compose this psi with a bisection that maps this guy to the interval 0, 1. So I make this psi into an L1 function, actually an L infinity function. Birkhoff average of a function which is invariant is the same function itself. And, well, the outcome is what I wanted. So once I have this 6 prime, then I will pick my function. So y is radon measures on EI. Psi of P is, by definition, mu bar IP. And then condition, okay, radon measures on EI quotient by this equivalence relation up to equality. This is still a nice Lebesgue space. And then I have naturally that condition 5 tells me there should be an S not here, or I should put, oh no, it's LS. Okay, good. So now I have to put 5 plus, no, 5 plus no one, 5. So I have psi, actually it's true for every S, I only care for S naught. So, but alpha S of P is, I really care about S naught because I want this. So this is equivalent, and in the actual space which I quotient by this relation is really equal to LS naught star mu bar IP, but LS naught is multiplication by 1, so it's identity. So this is mu bar IP. Maybe let me put brackets to mean I'm considering this relation here, just to make sure I'm not messing up. So this is the same as this, which is equal. So that's what 5 does. So then I can apply 6 prime with this to this psi. So this is psi of P. So when I apply 5 with 6 prime, I have this set inside R of full measure, blah, 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 so that have psi of P equals to psi of Q. So I get that if P belongs to this R psi S naught and Q belongs to WIP intersected R psi S naught, which is a set of full measures still inside here, then I have that mu bar IP is equivalent, because this equality is modulo this equivalence, mu bar IQ, which is equivalent to TPQ star mu bar IP by condition 4, 5, 6, 3, I guess. Yeah, 3. So I get this translation where TPQ is bringing, so it's a translation. So this tells us that TPQ is in GIP, and TPQ of 0 is essentially the guy corresponding to Q. Okay. So who is typically of 0. So now, how this completely solves our lemma? So the lemma will be solved when I do the statement, which essentially follows from the fact that this set has full measure. Let me write it here. That mu hat IP of R psi S naught complement is 0, and hence mu bar IP of HPI inverse of R psi S naught complement is 0. So now once I put these two things together, I get I have to show what? To show that this set has measure 0. So what I showed is, oh boy, what did I show? I showed that for every q bar in this set, I can find the translation that brings 0 to q bar, and that belongs to this group. Okay, let's write this down. So for every q bar in this HPI inverse of R psi S naught, there exists T in GIT such that T of 0 equals to q bar. Meaning that, so, and this implies q bar belongs to this orbit of P. And on the other hand, I'm saying that this guy has full measure. So what I showed is that OP complement is contained in the complement of this guy. And I know that this guy has 0 measure, and hence this guy has 0 measure. And then we won. So this is the lemma that says that the measure is actually supported on this orbit. So you have 0 measure to the complement. Now, see how much now this guy is telling us? Because now if the group were trivial, then this orbit is just 0. And then this means that the complement of 0 has 0 measure, which means that this measure is delta at 0. So this is telling us a lot. Now, the second possibility for a closed group is that this group be discrete, and then this measure will give you 0 measure to the complement of the scaled integers, and again, you will have 0 for the rest. And in the last situation, of course, OP will be all the AI, but then this measure is Lebesgue because, well, that requires some shop, but I will do it because I don't have an equality for the definition. I have this symbol for the definition, so it's not translation invariant measure, it's measures which are almost translation. So we will do it soon. You see that we are really very close to what we want. And actually, the following is a very important lemma. So it's just, I will formulate it really in the most abstract smooth ergodic series situation. It says the following: let f goes from x to x. X is a manifold, a compact manifold. Actually, it doesn't need to be compact. It's a manifold. Mu bar f diffeo. You need them at least 1 plus Hölder. If not, unless it could be only C1 if you have epsilon of knowledge, which is the unstable foliation, which we are essentially assuming. So I'm going to assume so C1 is enough, but I need to assume that mu bar is a measure, probability measure, F invariant. I don't want to assume ergodic, so I'm not assuming ergodic. And I assume, yes, that WU actually W so that we have a partition Wi, which is generated by in the form we had in the lemma, showing that there are conditional measures on these full partitions. So we want these box charts that allows us to do the things. So satisfying hypothesis of Rokhlin. Let me call second lemma. So the first is for the standard Rokhlin, the second is for the big guys. And if y is in Wi of x, then limit as n goes to minus infinity of log 1 over n log distance of fnx, fny is negative. So this is telling us that these w's are part of some unstable foliation in reasonably strong sense, because I want exponential convergence there. So once this is assumed, and I need to assume some extra property, which I can do here. This is because essentially I need to be able to apply Osseled's theorem and everyone else. I need that absolute value of log of norm df x be in L1 of this measure. So I think I don't need to assume anything else now. Then entropy for f is 0 if and only if mu p I hat is delta at p for almost every. So entropy 0 if and only if the conditional measure is atomic there. Okay. Implies. I'm sorry. The if and only if is if I further assume that this Wi is the full unstable foliation, then I have the other implication. So since I'm not assuming that this is the full unstable foliation, then it could be that this condition is atomic, but entropy comes from another direction, which is not atomic. So like in a product system, I could take the product F1 times F2, this on manifold M1, this on manifold M2. Here I have a beautiful Anosov system with positive entropy and Lebesgue measure, and here I just put Morse-Smale north-south pole map with no entropy at all. And then, well, I could have this unstable partition coming from here, from this coordinate part, which will have full delta atomic conditionals, and actually this is the guy contributing to entropy. So, but this implication is true and is what we care, I guess. Or maybe not. Okay, I think I need the other one as well. So if WIP is actually equal to this definition, the Q's such that this limit as n goes to minus infinity. And for this, I still need chassis 1. Okay, let me just be. I think I still only need C1, but let me put the welder just in case. We will see when it comes to the proof that will not be today. We will know it for sure. Okay. So if, moreover, we have the exact equality, and then this will be something that we'll have to discuss quite a bit, how to play with these statements. Then mu hat IP for mu almost every p implies h mu bar of f equals to 0. Okay, so then I have if and only if. Okay, so far so good. So we stated the Rokhlin lemma. That is a standard Rokhlin decomposition theorem. Then we stated a Rokhlin lemma for the long foliations, the non-measurable foliations, like the Wi. That's the second lemma we proved, so that's why I'm calling it second lemma. It's not that it's a standard name. So it's just and actually, it's not due to Rokhlin. So there are several versions. I think probably the oldest version of it, who knows? There is a very nice version of it due to Rudolph, another to Einsiedler-Lindenstrauss. Then I think Katok and Katok-Spatzier and probably Kali and Katok-Spatzier also have their versions. They are more or less. There are 2 or 3 ways of approaching it, and there is always the question of what is the more general way of doing it, which is not always the same. So when you have a dynamics like here, it's a little bit simpler to produce these conditional measures. You don't even need to require the hypothesis we pick when you have this expanding dynamics in this guy, on these foliations. But anyway. Okay, now the whole point of this is that this is relating us, finally, this hypothesis entropy we made on the measure with how these conditional measures look like. Okay, and now let's go back to where we stand. So remember, we assumed there exists some n in C squared such that alpha of n, so the entropy for mu of alpha, let's call it n1, was positive. Okay, now this implies, this is very easy, I will not do it. Actually, it's Abramov-Rokhlin lemma. For the suspension is also positive. And once we have that, we go to our picture. Say m bar is here. These guys are irrational, so it will not be in the boundary. If it were in the boundary, we could also play. There is not so bad thing. And here we make use of the fact that it's just 3 lines, 3 directions, and I have really full picture. We eventually will try to go over it, but let's say It's not here, so there is the N1. So let's assume that N1, and for definiteness, since I'm allowed to choose the order for 1, 2, and 3, I assume this is positive, this is negative, and this is negative. So 2 will have to be negative, and 1 will have to be positive. Okay. So hence, I take I equals to 1, and we have that mu1, so mu hat 1p is different from delta p for p almost every point. Okay, and moreover, I can make here and actually claim that this guy, this is an easy corollary of this statement actually, is that is not atomic. If it were atomic, the atom has to be delta p. And the same thing here, not atomic. So when you have one atom, the atom has to be directly. Okay, you see, I didn't assume ergodicity. What a pain. Okay, this. Okay, we'll do it later. So for ergodic measure, what I said is true. For non-ergodic measure, what I said is not true. I'm sorry. Because you could have a measure of positive entropy and add just delta at a fixed point. And then when you make this addition, you will have that the conditional measure for some values will have some atom because of this fixed point there. And the problem is ergodicity, but I don't want to assume ergodicity. I could assume for what I'm going to do now, but let's try to see if we can do it without assuming ergodicity. Okay? So I just know that this guy is not delta p. And so it may be atomic, but if it is atomic, it has at least 2 atoms for this N1. But then I applied it to, boy, the lemma I erased. Yes, the lemma whose proof was that. Because this fact implies that G1p is different from identity, because the orbit is not just 0, it's someone else. Okay, so this implies mu bar 1p is different from delta 0 for mu almost every p. And in particular, this cannot be just 0. You need to have some orbit. Okay. Now, let's lemma for mu almost every p, Gp1 is actually R. Proof. If Gp1, okay, let A be the piece such that Gp1 equals to R, alpha S and B be the P such that Gp1 equals to identity, and C is the complement of these two guys. Okay. Now observe that LS star GP1, which means I conjugate by LS, so maybe let me write it this way, of GP1 is equal to G alpha S of P1. Okay. And this is because of this. Because in coordinate this is dynamics, and actually not this, but where is it? This by 5. When I pushed one measure, so the LS from here to there, I bring the measure, and when I compose this translation by DLS plus the property on the HP, you get this. Now this observation tells me that sets A and B are alpha S invariant for every S. And since the measure mu bar is ergodic for the complete action alpha, this set has full measure or zero measure. And the entropy assumption tells me that this has zero measure, and I can hence assume by contradiction that this guy has zero measure. Now let alpha of P be such that, well, let's identify EI with R and translations on EI. We identify with EI, which is identified by with R, and we have the integers, which is our favorite lattice there. And so we define alpha of P is a very large number. Lambda of P, lambda was for the exponents. Oh, U of P, whatever. Positive B such that GIP is equal to U of S times Z for almost every U of P, not U of S. Okay, so it's, if it is not type A or type B, it has to be a lattice, and the lattices are all written like that. Then the observation over there is telling us that UI alpha S of P is equal to e to the chi1 of S times U of P for almost every S. Now the fact that U is constant, so if I take the S naught again, it's not so useful because I will have constant there, but I don't know alpha S naught is ergodic. So that's why I don't want to use that. On the contrary, I will take chi1 of S1 being, say, positive. I could take negative as well. It will be pretty much the same as well. And now I will go to Poincare recurrence. Okay? So let P be in an alpha. Let, so how is, okay, let me do this way. So let C be positive, let UC be the piece such that U of P is smaller than c. And then by Poincaré recurrence, for mu bar almost every p in UC, there exists ni going to infinity, so that alpha ni times S1 of p belongs to UC, and hence U alpha ni S1 of p is smaller than c, but this is e to the chi 1 n1 s or S1 ni times u of p. And since chi 1 of S1 was positive, this has to be 0. So u of p is 0, but u of p was positive. So that's impossible. So which implies that mu bar of u of z is 0. But u is measurable, so there is no way a measurable function of positive elements has 0 measure, so it's unbounded. So no contradiction. And the contradiction is that, well, one of these two guys has to be full measure, and entropy test is not this guy, so it is this guy. Okay, now I need 2 seconds to finish, which I don't have it, but just give it to me. And I will do now the easy finished, and then we are still going to argue further on Wednesday when we start abstracting all these, and then we have to really get more information. But now we can finish quite easily. So first, so we worked so hard to show that G1P is essentially R, and hence we have that for every T in R, T sub T star mu 1P is equal to C sub T mu 1 bar P. So that's what we get. Then it's easy to see that C, which is now a function from R to actually R plus, it has to be e to the alpha t beta t for some beta in R. Because this is a group homomorphism, so it just follows from the very definition. And these are the only group of homomorphism from additive to multiplicative group, and it's a continuous group of homomorphism. So that's what you have. And once you know that, this implies that mu bar 1p is up to a multiple e to the, I may be wrong, but I think it's this, e to the minus to this measure. And this is really not hard to prove. So you define mu equals to e to the beta t or e to the at mu bar 1p, so this Radon-Nikodym derivative, and then you find the a that will kill the beta here, and then you get a full invariant measure. We think that nu is Lebesgue because it's fully translation invariant, and hence the mu bar will have nu 2 times e to the minus a. And the correct choice of a, I think, is again beta, but it could be minus beta. But it just solves the equation. It's a trivial equation to solve. Okay, so this shows that this is the measure. It's not yet dt, but it's almost dt. Now, again, you do some Poincaré recurrence theorem plus some continuity. I will not do it because we really run out of time now. But you take your point P, you know that this part of the guy, let's say beta is positive, then it tells you that this part has finite measure, and even more, when you chop down here, it has very tiny measure. So not just finite. And then you go again to Poincaré recurrence. Poincaré recurrence, since the conditional measures are fully supported, tell me that P will come back down here, then this measure will have to come to that place here, but now you are losing really a lot of measure because even this guy will go up here, so this very tiny measure will have to correspond to this very tiny measure, but this is already large measure. And then this you will get a contradiction. This again a Poincaré recurrence statement. There is a second proof, which is a little bit better, that comes in Ledrappier-Young and is very natural in Pesin theory, that tells you that once you know that the conditional measure is absolutely continuous, you also know what is the Radon-Nikodym derivative. And the Radon-Nikodym derivative is given by the product of I larger than or equal to 0 of the unstable Jacobian divided by the unstable Jacobian. This is on P and minus IP. This is, and this is times dt is supposed to be this guy up to some number. This is again, this is what Pesin tells you, that once you know the conditional measure is absolutely continuous, actually the Radon-Nikodym derivative is given by this formula. And now in our situation, this is a number that is independent on the P or on the Q, is e to the chi1 of the S you are choosing. And then this cancels out, so you really are getting dt, not anything different. So this is the second way. So this is telling me that actually beta is 0, this does not exist, and the mu bar 1 is actually dt. And then just to finish, what does that imply? This implies that when I bring things back to the torus T3, I have my W1 foliation and the measure mu, and when I disintegrate the measure mu along the W1 foliation, it is dt. Now the W1 foliation is actually a flow, a linear flow, and the fact that the conditional measure is dt, it means that this measure mu is invariant by this linear flow. But this is an irrational linear flow, and there is only one measure which is invariant by this irrational linear flow, which is Lebesgue on the torus. So let's choose Lebesgue on the torus, and that's what we were supposed to prove. So this finishes with everything. Now what we are going to do in Wednesday is start abstracting everything. We will not be able to do this last part of the argument. We will not want to do this recurrence Poincaré recurrence argument. We will really push to this argument to know what is the Radon-Nikodym derivative. And instead of doing this, knowing irrational flows, which we may use actually something like that eventually, we also will want to use the fact that once I know the condition along W1, then I move to W2, and the W2 measure will be either Lebesgue or atomic. If it is Lebesgue, then I will have Lebesgue on this plane. If it is atomic, I will have to prove that the conditional measure along this plane is actually Lebesgue on this line. And this is already giving me information. And then start really building the measure by knowing what happens with each conditional measure along each direction. So that is more useful in the a little bit more abstract situation. So that's what we are going to do, even though we are very close with just playing what we are playing here to the normal subgroup theorem. So we are really probably, yeah, maybe on Wednesday, instead of doing the full abstraction, I will relate all this proof with the normal subgroup theorem proof and then we do the abstraction and just cook up everything. Okay, thank you. What I plan to do today is two things. One is to try to see how what we have done so far fits into this normal subgroup theorem, and then we will have to address this ergodicity issue that led us to the pi partition trick, that in our situation here, the pi partition trick will not be available, so we need to do something else. And still in this case will be an easy solution, so it will not kill us. So it comes to a more general situation where this really is impossible to, well, not impossible, but it's very hard to do. So, well, let's see where we stand. So I will not reveal the whole reduction of the normal subgroup theorem. I just will put the setting which we reach essentially. So we had this space maybe we have this factor theorem, so we have this H from P mod G into X, where we have the lattice acting in both places, here by alpha, here in a natural way. We build from this guy X to the alpha the suspension, and we build a measure here mu, which is essentially the graph of H. Okay, and essentially the graph of H means that this H induces an H hat from G into X. So the graph of H hat is a subset of G times X. And now we define on this guy, essentially Lebesgue measure push on the graph. So we push Haar measure on G to graph of H hat. Okay, so, and if I put symbols, it's very easy to define, but I really want you to think in these very geometric terms. Okay, and yeah, the actual definition is the integral of phi d mu is, well, first d mu hat of gx d mu hat of gx is nothing but the integral of g h hat of g dg for phi some compactly supported function on this product space, and then this is pretty well defined. And then we can check the equivariance here of H will imply that if I restrict to a fundamental domain, this gives me a well-defined measure mu on the quotient space. And so we have this projection here into G mod gamma. We have the G action here now, the corresponding G action up here, and we have the natural quotient here. Then when I restrict to P, we have that the measure mu is P invariant now. That's because I have the mod P here. And of course, oops, here is G mod gamma. Yep, with standard Haar measure. Moreover, if we define, as we did before, Q was all the G such that alpha G star mu equals to mu, then this is contains P is a closed subgroup and we can actually induce the Q measure on there. H will be coming from the mod Q actually, because the G invariance of the measure mu is related to the equivariance of this graph when you play this game up there. So it allows me to define actually with the same letter Q mod G still into X and still does the job. And so all this picture I can do it directly with the Q, even though most likely Q is equal to P, but the point of this is just optimize the starting point, and we do, I just repeat essentially what was above, have this is covering this, and this is this projection pi. Now the first observation, which is very important, and this will help us solving a lot of the issues which would appear later in Katok-Spatzier and even later, is that this pi is an isomorphism. Okay, so it's a one-to-one bijective mapping mu to Lebesgue. So the fact that it maps mu to Lebesgue is by definition, okay, because just define the dg. So if phi doesn't depend on the second coordinate, the dimensions come Lebesgue. The fact that it's one-to-one is because H is the graph, and then naturally the projection is one-to-one from the graph into the first coordinate. The projection from the graph into the second coordinate may fail to be one-to-one. And it's actually, there is where the discussion of how injective is H. But the projection into the first coordinate is one-to-one. And here we are talking about projection into the first coordinate, G. And this is a one-to-one. So which means that this is an isomorphism.
Isomorphism in the measurable sense.
Yeah, yeah. So it's a bisection mapping measure to measure and conjugating actually the G action with the G action, even though the measure is only invariant by the Q, but the conjugancy happens for all the G action. And then let me remind you that what we said is all our task is about the injectivity of this H, which is also projection to the second coordinate. And injectivity of this guy has to do of the intersection of the level sets, horizontal level sets, which are G times X, which will be called differently in a second, and the vertical, and the graph of H. Okay, so that's what discussed, and these sets are Q saturated. That's the Q invariance. And the question is there anything else? And what we really would like to prove is that this is exactly the same as Q times X, because if we can prove that this is true, then you have that this quotient is injective. And what we are going to do is to do that in terms of measures rather than of sets. So we will take the conditional measure. So the measure itself, mu, is supported in the graph. Then we condition it to the G orbit, and we want it to be the same as the measure on the Q orbit. So lemma 1 is, okay, before lemma 1, I said that this actually, I will call it O G of the point. In this case, doesn't matter which point because all are in the same orbit, that is of some point. And this is the G orbit because we have the G action, so this is the G orbit there. This is the orbit for Q of this point, which I'm putting it in brackets, but actually this picture is happening in G times X without the quotient. So let me do the abuse of language there. And instead of graph, this will become the measure mu. Okay? Now, it's important to play both sides here. Okay? So one side, the measure mu is like the graph of h hat. The graph of h hat is very unwrapped in G times X, so it's really everything beautiful. But then when I go to the quotient, this measure mu get whatever wrapped, and so it's a dust of points, which doesn't look really like a graph anymore. Okay? At the end of the day, actually, it will look really as a graph, but by the time being, it's very hard to see this dust of points. Yet we can define, so we can disintegrate using Rokhlin second lemma. Okay, mu, and now it is on X alpha along the G orbits. That's why it's the second lemma. If not, I would use the first lemma. So mu G P and also I can do this disintegration. Now the partition into Q orbits further refines the partition into G orbits, which means that actually this measure itself is disintegrated by these measures. Now the first lemma is easy, says that for mu almost every p, mu qp is, well, yeah, it's equal actually to Haar on Q. Okay, we're here. Actually, as always, we should use this notation because this measure we only know them up to a factor, even though Haar measure we also know it only up to a factor. So we don't know Haar measure. Haar measure is not well defined with normalizations, where we identify the Q orbit of P with Q by the natural parametrization of the orbit by Q. So yeah. Okay. So I didn't mention it, but I leave it to you. The claim is that for almost every P, this parameterization is actually injective. Okay, and this, assuming Q is not G, because if Q is G, we don't need anything to do. And this is the fact that Q is not hitting the lattice. So the orbit of Q cannot hit the lattice, essentially. So, and that's just because. Yeah, actually I put E here. Maybe I won't really put G here. Because here nothing changed, but here things may change. But and then here is not actually Q, it's some translate of Q, but anyway. So because we don't know where is exactly the guy. Okay. Now the proof is just, I will not write down, but I will let it for you. It's just about taking compactly supported functions and lifting things upstairs, essentially, and is Q invariance of mu. And actually, it follows from a more general lemma that I would like to maybe state very full generality. So let us take G naught acting on space X. Yeah, so just like this. Mu a probability measure on X, and assume this action. Actually, the induced foliation rather than the action, but we have the action satisfies hypothesis in Rokhlin's second lemma. And remember, the hypothesis is the fact that you have the long tubular neighborhoods for the orbits. So that's what it is. Then alpha preserves mu if and only if mu G naught P is equivalent to Haar on G naught for almost every P. Okay, so we're using this in this case of Q, G naught equals to Q, but that's a completely general statement. So preserving a measure is the same as the conditional measures being the Haar measure on the corresponding place. So when the group is the integers, we are saying that you have counting measure along the orbits of the guy. When it is the real, is dt. When it's general, is Haar measure. So we want G naught to be locally compact. How so? And the action to be continuous in the G parameter to make sense. And then the proof is just this. And this is the proof of this is essentially the uniqueness of Rokhlin decomposition. So you take Rokhlin decomposition locally and just put Haar measure. So Rokhlin will give you some family of conditional measures and some transverse measure. Now you remove your transverse measure, you keep the transverse measure, remove the conditional measure, and put the Haar measure. And then you will check that it works as a decomposition due to the invariance of the measure mu. And the uniqueness of the decomposition then tells you that these are the same guy. So this shows that if the measure mu is invariant, then you have the equivalence here, and for the other implication is should be pretty much the same. Essentially, it should be that if I do Rokhlin decomposition for this guy, the way it affects the conditional measure is by shifting them by the G, but then since we know that this is equal to mu, then you will have that this guy is proportional to the other measure, and then a trick, the way I did it last time, will tell you that, well, it's true that they will not be invariant by translation, will be proportional to the other guy, but that's pretty much should do the job. Yeah, maybe I will go back later if I have time today to this proportionality issue. Anyway, okay, so this tells you that we have Haar along the Q orbit. So, which means that when I take now these measures, we have on the G orbit of P, then this G orbit of P is foliated by the Q orbits. And when I disintegrate these along the Q orbits, I get Lebesgue on these Q orbits, and transversely I get something. And what I want to claim is that transversely I get nothing else. And that's exactly what this means. Okay, so the key lemma to that statement is that for mu almost every p, mu gp is the same as mu qp. So, which is supported in much thinner place, so it's not seeing anyone else, and this essentially becomes this statement which gives you the injectivity. Not only that, I don't need to say because it's exactly what we discussed in the previous lemma. The right-hand side is Lebesgue on this Q guy. It's a very nicely homogeneous measure. And there is where also the game starts, because I'm trying to show that this guy looks like a nicely homogeneous measure on some subgroup which is called Q, and actually I don't care in which subgroup. So I did my definition of Q because it helped me to understand what we are looking for. But forget about this definition of Q. What I want to show is that this measure is Lebesgue measure on some subgroup. That's what I want. And once I know it's Lebesgue measure on this subgroup, then I will have whatever invariance and everything just comes again for the same lemma. Now the good news is that what we did last week, and probably a little bit before as well, we discussed how to prove a measure is Lebesgue. And now we are going to use it here. So for the finite, let me do things in dimension 3. Okay. So I have my matrix here. I have P. And I know I have invariance by P. So it means that along all these one parameter subgroups, the measure is invariant. Now, let's consider this one parameter subgroup. Okay, so let's call it G. Should I call it G or E? I think it's also standard notation. And it's 2, 3, no? This matrix is 1, 0, 0, 0, 1, 0, 0, T1. Okay, it's a one parameter subgroup, so it induces a flow on that space. And I would like to show, I will have to fail, but I want to show that when I do mu along this E23 direction, oops, at T, now this is Haar. Actually, it's TT because Haar there is DT. I want to show that. And as I said, I will fail because it's if this guy is not in Q, there is no way this is DT. Okay? But I want to show this is DT, and then in this way I put this guy inside Q. And since I'm saying I'm going to fail, I want to see what I get after the failure and what I can do about it. So let's see what I get. So I put the machinery. We have our R2 action on X, which is not this guy. My R2 action, so these guys, the orbit of these guys will be like the Wi. The R2 action, which we are the A and B commuting, is this e to the t1, e to the t2, e to the t3, 0, 0 on x alpha, t1 plus t2 plus t3 equals to 0. I have this action here. And then I have the exponents chi1, well, chi2, 3, corresponding to this. And I have my parametrizations h sub 2, 3 from R into the 2, 3 orbits of P, which is inside x alpha, which is h23 of P, is e23 or alpha on e23 of P applied to P. And this is, I don't want to claim it's smooth. It is continuous. It's not even important that it is continuous, but it is continuous if I assume that X were a compact metric space and alpha is continuous. Then this is continuous and is injective. And that's all I want to know. But what I really care is about our diagram, like the last time, of T. Yes, and I should have the P somewhere. So it's 2, 3, P of T. Okay, thanks. Which this maybe I call it W23 of P, just to emphasize the analogy with our previous situation. And what I have is the diagram. And here I have W23 of P. Here is W23 of the translated guy, E23 P of P. No, not of this. I'm sorry, of alpha of T1, T2, T3 of P. And here I'm abusing language. Maybe let's not abuse so much language. Let's put D sub T1, T2, T3 of P. And this is the matrix D1, T2, T3. So I have this matrix. And here is this alpha of D, blah, 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 maps here to here. Here I have my parameterization on alpha D, T1, T2, T3 of P. Here I have parameterization of P. And down here, what I have is multiplication by e to the chi23 of T1, well, of D, T1, T2, T3. And this multiplication is nothing but e to the T2 minus T3. Okay, and this is all just making the computation. Okay, and actually, if you see what is the parameterization and what is the action, what I'm just saying is that what I get here at the end of the day, before doing the full identification of where T is mapped with R, what I'm considering is alpha of so let's see. I go first with e to the e23 of T. Then I apply the T1, T2, T3. And then I want this to be alpha of e to 3 of s, and this s is who is, and then of this apply to p of dt1, t2, t3 of p. Okay, because I have my p here, alpha dt1, t2, t3 of p. I taking one point here, which is this e of blah 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 of t. I'm flowing this guy onto here, okay? And I want to know how is this the same as doing this and that. And this is the s. So if this is t, this is s. And solving this formula tells me what is s. Okay, now solving this formula, I can forget about the p's and the alphas because the alpha, as I said, is injective, whatever we care. So this is telling me e to the t1, e to the t2, e to the t3 times 1, 0, 0, t, 1, 1, all 0 is similarly s 0, 0, and here the diagonal. E to the t1, e to the t3, e to the t2. And this is just the product of three matrices, which are very easy to compute. And if I did things correctly, I should be getting t2 minus t3, if not t3 minus t2. It probably should be t3 minus t2.
Because when you conjugate upper triangulars, you get t2 minus t3.
Yes. So this with this nothing, and I get st2, and then is t3 minus t2. You are completely right. Where was t3 minus t2? Here. Which is actually yes, because this is the position. It's not 2, 3, it's a 3, 2 position. No, it's third row, second column. So it's the 3, 2 position, not the 2, 3 position. But what? I will not erase all the 2, 3 into 3, 2s. Okay, anyway, but this multiplication by this number, which is this chi 2, 3 of t1, t2, t3, which is t3 minus t2. And actually, in all this picture, I have the other Lyapunov exponents and the other invariant directions, which correspond to each of the stars out here, with the corresponding Lyapunov exponent. And I have the Weil chamber picture as we had before. Which is this chi ij equals to ti minus tj, and of t1, t2, t3 is ti minus tj. And one important observation which destroys the bipartition trick is this fact that when I make one, then I lose the other. Because this doesn't allow me to do the bipartition trick. Because when I sit here and I may move to this direction, then the ij direction so becomes, say, stable, but then the ji direction becomes unstable. And then there is no preservation of the stable or the unstable. Both are changing. And then this does not allow me to do bipartition. This is not really a problem in this situation. In other situations where you try to do the same trick, it is a problem if you are not in my setting.
So is this the failure of totally non-simplicity?
Exactly. And this is very natural. Actually, totally non-simplicity is a huge assumption, because for most representations, if you are in algebraic world, you will have this type of thing. So you will have them. So it's unavoidable, actually. So you have really to know what to do with this. There are some few cases where you don't have it, but it's really very, very few. Anyway, so how we deal with this? So we are not going to do bipartition, but let me recap what I want to do. So I have all the same now framework as before. I have these mu23 p measures. I can define now these mu23 p bar measures on R, and then I can just continue the proof as I did before. And I get two possibilities. Possibility 1, mu bar 23p is proportional to dt, or 2, mu bar 23p is delta p. According whether that group was, so remember the whole point is you take the group of translations of the real that leave this measure mu bar invariant. This group is a closed group, so it's either the reals, trivial, or a lattice. We saw that it cannot be a lattice ever, so it's just delta or here. For this, I need ergodicity, because I need a bipartition tree. So this goes in this lemma that says if T2 equals to T3, so in this T2 minus T3 situation, or T3 minus T2 situation, then alpha of T1 is ergodic. So mu is ergodic. So I don't have a partition tree, but I have ergodicity. And ergodicity is even better than bipartition tree. Okay, so then once I have ergodicity, then I really have that it's either this guy or this guy. If I have this, I'm happy. I put this direction inside Q, and then I can move to the next empty slot. If this is delta, I'm not so happy. I just mark it for a while, and I move to the next empty slot.
So I have a question.
Yes.
This time space that you drew is associated to the diagonal action, which is an R2 action.
Yes.
But then the time space of G should be 8 dimensions.
Is L2, yeah, is L2 is these dimensions. Yes. I have this 8 dimension, which is 9 under the constitution determinant is 1. So yes. So I restrict to the R2 action, which is the diagonal action. And when I restrict to the diagonal action, I have my total space, which doesn't have dimension because in the x direction is who knows what. I'm not going to analyze the x direction because I cannot. So you don't do it. You only analyze what happens in the g directions, in the orbit direction. And in the orbit direction, you are very smooth. You are whatever you want. You are algebraic. You are part of the group action. Okay? So in this g direction, I have these 6 other directions. So I have the orbit direction, these are 2. These are useless. They commute with the diagonal. Okay? So we don't analyze them the same way we didn't analyze in the case of the torus. When we went to the suspension. You analyze what is perpendicular to the R2 orbits. And perpendicular to the R2 orbits are these 6 directions. Now, for these 6 directions, I have the 3 upper ones, which I could do whatever we are doing here for these 3 upper ones, but I already know they are dt. So I will just produce dt and nothing else. Now, for the other 3 guys, I produce either dt or p, or delta. Okay? Now here, there is one information. I will not fully exploit it now because I want to concentrate the rest of the day to prove the ergodicity lemma there. But observe the following. So let's say this one is dt. Then I have the 2 other ones. If either this is dt or this is dt, then I'm done. Because there is no group that contains all but one of the elements. Okay? So this comes in the general situation as the classification of parabolic subgroups, so which we discussed. So whenever you contain the P, you have this sort of staircase picture. So, and not any staircase picture is possible. So this one is not possible. So there is some bracket business where it tells you, I don't know how it is, but some guy has to be smaller than some other guy. Okay, so either the three are dt, or I have delta in these three directions, or I have delta in these two directions. But then I have to improve a little bit, and that's what we are going to do later. And part of the game is that the complement of Q, let's say we are in this situation, is also a group. Okay? And now we are going to show not just that the measure here is delta and the measure here is delta, we are going to show that when I condition to these two guys, the measure is delta. And once we show that when we condition to these two guys, the measure is delta, then it will follow that the measure actually lies in the complete Q. Okay? So that's what we need to do more than what we have done in dimension in the case of the torus.
So when you say complement of Q, that means that you're looking at those elements that don't fix mu.
Is more than, so yes, but is more than that because I want a transverse group.
I see.
And here I can do it because I have this. And this is also true in any semi-simple group situation. So you have this, the classification of the parabolic groups is given by roots. And you have these roots are the guys not entering into the parabolic group. And this gives you the complementary group. Okay?
And also, do you define this chi23 as the kernel of E23?
Yeah, yeah, exactly.
So that's a six-dimensional.
No, the E23 is a one-dimensional space.
No, the kernel.
The kernel is, no, I mean R2, so the kernel is a one-dimensional space.
Okay, okay, I see.
So, yeah, maybe, okay. No, yeah, I said yes and I was not yes. So how you define E23? Okay, so this comes from the theory of roots in Lie groups, so which we are going to discuss later, but let me just do it here quickly. So we have your Cartan subgroup, and A will belong to the Cartan subgroup, and actually to the Lie algebra of the Cartan subgroup, the Cartan algebra. You bracket it with H. H is some guy. I don't know who it is. And I want this to be chi I of H. And if I put here H such that this is what is defined, and this should be for every A in A. And you define this as E of chi. Okay? These are all the H doing that. That's what it has to do. So for most chi, this is trivial, it's empty. Well, just have the zero vector. The magic is that for some chi's, this is non-trivial. And that's the case of 2, 3. If I put the 2, 3 here, then I get the 2, 3, and these H are these matrices I put there. And this computation there becomes in the Lie algebra level, this computational relation over there. And that's how you define the root spaces. So, so for every chi here is a functional, so it's in this Lie algebra of A, is in the dual of this guy. And for every functional, you define this E chi, then you show that there are only finitely many guys, and you also show that your Lie algebra of G is the sum of these E chi over all possible functionals. Again, most of these guys are trivial, only finitely many non-trivial, plus the Lie algebra of A. You want chi different from 0 because if chi is 0, then you will be having the Lie algebra of A here, plus which is the M, which is the 0 exponent essentially, which corresponds to the chi equals to 0, which is the guys commuting with the Cartan, but not being in the A.
That's a centralizer. So when you,
yeah.
Okay.
So this on top of it coincide with the element in the compact commuting with A, but it's also. So, and this is true for a, I hope I'm not forgetting anything, but this is true for any Lie group. You have this full decomposition. Or any semi-simple Lie group. And then once you have this, whatever we have done so far in the discussion essentially can be done for each of these chi. We will have the W chi, and these are sometimes could be two-dimensional. It's true. There are some complex issues and things that goes beyond my knowledge, but in any event, you will have that the measure is whatever Lebesgue there or not, or atomic. Let's say they are all one-dimensional, and then we still need to discuss how to start putting them together. When you take not just one dimension, you start putting e to 3 plus e this guy or this plus this or any two guys that could be added, what we do with that. But now I want to concentrate about this ergodicity. Okay? Which, okay, I have 10 minutes, maybe less than 10 minutes, 5 minutes. So, but at least I want to state the theorem, and we are going to prove it on Friday. And then we go back to our factor theorem, because there is still quite a bit of things to develop, but we are now, I think, by now we really know how things are going on here. So how we go from the factor theorem to from the normal subgroup to factor, how the measure rigidity or rigidity of measures comes into play. And now we just need to play more geometric fact about these measures. But we need this ergodicity. So observation before we start is, remember what I said, when I have this measure here, this guy is isomorphic for the P, is isomorphic to the P action on G mod gamma with Haar measure. Okay? Now this element I'm writing here belongs to P. So, and since these guys are isomorphic, ergodicity here is the same as ergodicity here. So I only need to prove ergodicity here, which really makes it simpler than proving ergodicity anywhere, even though at the end of the day, we will see that it's not such much. Well, there is quite a bit of difference because I don't have the G action here. I only have the P action. Well, I have the G action here. I don't have that mu is invariant by the whole G action. Okay, I only have invariance by the P, which would make things harder to translate the proof from there. While here I have the whole G action preserving lambda, and this is simpler to play. So the theorem is Howe-Moore's theorem, which gives you more than ergodicity. It tells you the following. I will only do it for SLNR. It's true essentially in huge abstract generality, but let's just do it in SLNR. It says the following. So let P from G, so we call it G, into unitary operators of a Hilbert space. So this is unitary of H Hilbert, and is as always the continuous in the strong sense. So if Gn goes to G and X is in H, then by Gn X goes, let's do it this way, minus by Gx goes to 0. Okay, so it's nicely continuous. And assume pi has no invariant vectors. Again, this is very easy to achieve because you take the set invariant of pi is a closed subspace of H, and then you take the perpendicular of this since these are unitary operator, this is invariant, the perpendicular is also invariant, then you restrict to this other representation, and then you apply to this other representation. And you write any vector that I'm going to write as x plus x bar, and here nothing changed, and this will happen, whatever will happen now. Then if Gn goes to infinity, meaning it just leave every compact there, then pi Gn of x goes to 0. Actually, I think that's the way you write it. So weakly for every x in H, which is mixing property. So this trace pi Gn of x dot y goes to 0 for every x and y. So that's equivalent statement to this. So that's mixing or decay of matrix coefficient, or just Howe-Moore's theorem, which implies ergodicity. Okay, so as soon as the guys goes to infinity, and when I take the iterates of these guys, alpha dt1, t3 to the n, actually this guy goes to infinity as soon as they are not all 0. So this goes to infinity, which means that this element is mixing, so in particular it is ergodic. So this lemma is consequence of this Howe-Moore theorem. Now the Howe-Moore theorem has two ingredients. One is Maundner phenomena, and the other is, let me write down the Maundner phenomena, which is also very useful. No, that's part of the game, is that you really don't care at all. Even though in our situation it goes in a very precise form, the real power here is you have no clue. We will see in the proof how this reduces. Okay. I want to say something about it. Yeah, there is no rate here on how fast is this mixing, even though there are other consequences and other proofs which eventually leads you to rates. So if you assume x is not just on the Hilbert space, but are smooth vector, whatever it means to be smooth vectors on this Hilbert space, if you imagine that H are, so if you take gamma co-compact and then H is this guy, and then you have the natural action, then if you take C1 vectors instead of L2 vectors, then you have even rate of convergence here. This follows from some enhanced versions of the proof of these guys. And in general, you can define on the Hilbert space what are the smooth vectors. One will be smooth vector with respect to this guy, and the way you do it essentially is pi is some unitary guys. You do the spectral theorem to pi, to the elements of pi, actually pi restricted to the Cartan subgroup. From there, you can essentially cook up a Laplacian along the G orbit, and then you do the same you do with Sobolev spaces. So these are the vectors where you can differentiate along the G orbit, essentially, and belonging to H, the derivatives. And then under this assumption, you still will have something like that, if things are correctly, as always. Okay, so what is Maundner phenomena? I will try to write it in this very, very full generality. We only were going to use in the case of SL2R, which is much simpler, but I will try to write it in the most general situation. So says the following: let again pi from G into this will be unitary representation. Here G is just locally compact, also blah blah, nothing else. You could even have invariant vectors for this matter, so we don't care. And let H be a vector in G, which eventually will be something like the E to 3, essentially. And let AN in G be such that AN H, AN inverse goes to 1. Well, 1 is identity. Okay? And assume pi AN of C goes weakly, of X goes weakly to C for some X in H. Then pi H of C. So the limiting guy is an invariant vector for H. Not for the sequence AN, but for the. Okay, so that's how you can read this in a sense. So there are several important readings of this. One is this fact we know from Anosov systems is that if a function is invariant by the hyperbolic dynamics, then the function is constant along stables or constant along unstables, which come from Birkhoff ergodic theorem, essentially. So imagine that X were invariant by AN, and AN is your diagonal dynamics, then it means that X equals to Z. And then the guy doing that are exactly the stable or unstables, depending on how things are written, directions for this expansion inside the geometry. And then what you are saying is that if the function is invariant by the diagonal, then it's also invariant by the unstable. Unstable because also the stable, because if the guy is invariant, then I could use the inverse of n, and then the h that will appear also they go into the other direction. So that's the mostly dynamical version of this. But is much stronger in a sense than this statement, because we don't know much knowledge of an. We don't need to know any invariance of x. We just have in this limit. Now, about how to reach this limit is not so hard, because it's only with conversions that we care. And remember that since it's unitary, all these vectors have the same norm, and the unit ball is compact. So you have conversion subsequences. You have plenty of conversion subsequences. Now the limit will be in the ball, so most likely the C will be 0, and that's what we are willing to show. So we want to apply essentially here. We will not be doing what I'm going to say now, but something very close. We take a weak limit of this sequence. I want this weak limit to be 0. Okay? And then we will do a trick to swap from Gn to An and take this weak limit again. And this weak limit will be the C. For some An, which will correspond to diagonals, then we will look the H, which are the unstable or the stable guys for this sequence of An. We will get that they are invariant for along the unstables. And once we have invariance along the unstable, we will keep on pushing unstables there, and then we will show invariance by the diagonal. Then we will show invariant by everybody. And that's it. That's how Howe-Moore is proved. And I think the very original proof is essentially that one. And that's what we are going to show. And then we get ergodicity. So we are going to do this on Friday. And then next week, we'll go back to measure rigidity and try to do the more than one-dimensional spaces when you put two root spaces together, W1 and W2, and we still want to prove this measure is atomic there. Okay. C'est tout. Okay, so let's see where we stand. So we want to prove this Howe-Moore, which will give us ergodicity, and also the proof is in the same direction of the proof of property T for the same sort of groups in the case of SNR. So maybe we can discuss on Monday property T as well and get the proof of property T for SLNR, just following the same Howe-Moore type of trick. Okay, so what this says, it says that so we have G equals to SLNR pi from G into unitary of H. So strongly continuous, meaning that if Gn goes to G, then pi Gn x minus pi Gx goes to 0 for every x in H. Okay, so that's the type of continuity we want for this representation, which is typically standard assumption. Then assume pi has no invariant vectors. Then for every psi or dw in H and Gn going to infinity, pi Gn b dot w goes to 0. Okay, so it's mixing property, sometimes called decay of matrix coefficients as well, for these guys. So certainly you need the no invariant vectors, because if not, you take the invariant vectors with itself, you will not get to 0. But you can always get into the orthogonal complements of invariant vectors and apply this to this orthogonal complement. So in general, what you get is the standard mixing way. Well, you have to project into invariant vector, but it will be something this times w minus projection of b times projection of w. This goes to 0. Something like that. Okay? Or projection is projection into invariant vectors. Anyway. So the proof goes, the first step is mountain phenomenon. Which is, so let G naught be locally compact Hausdorff. It's just to claim is for very general group, not just for G. That's why I'm calling it G naught.
What does it mean to in general Gn tends to infinity?
Oh, okay, yeah, this, so G is SLNR, so I'm just doing SLNR, and then it means it gets out from any compact set in SLNR, or you can put it, if you put the matrix norm, it's, so here is, you can just think in this way, and this is perfectly accurate. Yeah, in general, the best way is to just ask to get out of every compact set, and that would be. Yeah, there are eventually, I don't think we will get so deep into lattices, but there are, when on the quotient spaces ways of going to infinity that are more delicate, and what the precise meaning is really very important. But at least not now, we are not going now through these subtleties. So here it is really one entry of the matrix is going to infinity. So that's really what it is. So good. So we have this locally compact guy. we have again one representation and the same continuity property. And we assume A sub n in G naught and H are such that an inverse H an goes to identity. Okay, let me see if I'm taking the inverses in the right way. Yeah, I think that's the way. If not, I just will get for the inverse. Doesn't matter. Now let Z belongs to H, or X belongs to H, be any vector, and assume pi an of X goes weakly to some guy. Then pi of Z, pi H of Z equals to C. So Z is invariant for the H guy. So this is weak convergence. Which is pretty much like this type of conversion. And this is really the core of Howe-Moore, plus of course you have to do a lot of things because you start getting some invariance for the limiting guy. So a different way of stating this Howe-Moore would be to say that pi gn of B goes weakly to 0 for every B. Okay, and then essentially what is behind, I'm assuming no invariant vectors, so that it should go to an invariant vector, or even here in Maunder, assuming that there is no invariant vector, I would like Z to be 0, but then I really will not be able to get it that easy. So, because G naught is just an abstract group here. That's why it's such a different statement, but they are really talking about the same subject. So let's prove Mautner, and then we go back to Howe-Moore. Okay, let me see if I remember how to prove Mautner. It's really not hard. You can always suggest, but I guess it's just putting these two things together essentially. So if I take this, apply to Z, or apply to X, I'm sorry. If I apply this to X, not sure why it should go to, oh yeah, it's okay. So this, here is important to keep the thing, so this goes to 0. Okay. Now I want to compare very similarly pi of HAN X minus pi AN of X. And the claim is that this also goes to 0. And in norm it goes to 0 because it's an unitary guy, so this is just taking pi of AN inverse. AN of X now I think is, and is HN, and now I think is correct. And yeah, so this is because I'm just taking the multiplying this by AN inverse, I get the previous expression, and this is unitary, so it doesn't change the norm. Good. Now, this is the same as pi h, pi a and x, which is still going to 0. And now I'm in very good shape, even though I have to argue, because this guy is going to z and this guy is going to z. But it only goes weakly, not strongly. And it's important that I can do it weakly, not strongly. So then I have to argue that still pH of C equals to C. So the norm of I want to argue that this norm is 0 due to this fact above here. Okay, so now one have to be a little bit careful, but there is evidence enough now of what we have to do. So we take pi h of z minus c with pi hc. Let's try to do it this way. And now instead of I want to compare this and hope life is nice with the maybe simpler. Instead of putting, let me put in the second coordinate just any vector v, and I will show this is 0 for any vector v. Probably it's much simpler. Notation is simpler. Now I will compare with the pi a n of x. So I just add and subtract this guy. This minus this times b plus pi h pi a n minus pi a n x dot v. Okay, I just added and subtracted this guy times v. Now this guy, the second guy, goes to 0 because it's dominated by this times the norm of b, and this is Cauchy-Schwarz. So it's strong convergence implies weak convergence. And for the first guy, I now group the guys together, and I get pi of h times z minus pi a n x minus z. Actually, if you allow me, I can put here just pi of h minus identity times this guy. This gives me this expression up here dot v plus this guy that was already going to 0. Okay, I think I didn't want it to do what I did, even though I can survive with it. So this is equal to z minus pi a n x dot pi h minus identity star of b plus the guy going to 0. And now this is a vector as any other vector, and the weak convergence of this guy to z tells me that this is still going to 0. Good. That's really analysis. It's very basic and simple analysis, but it has a huge implication in here. So this is Mautner. Now, how we use Mautner to our business, so we have to find a lot of h's doing our shop. At least one to begin with. And for this, we also need to find the sequence an. So that's the first thing we are going to do, is to find a sequence an and an h doing this way. So for this, we have the KAK decomposition, also known as Cartan decomposition. Also known as Cartan. Which essentially says that G can be written as KAK, where K is orthogonal and A is, as always, diagonal. So it's e to the t1, e to the t. I think it's the one that is below the thingy. That one, yes. Oops, no, not that one then. Then screen light. Okay, good. So this, for in general semi-simple group, is this fancy Cartan decomposition, KK decomposition. The proof is the same as the linear algebra decomposition that tells you that any matrix can be written as a positive matrix times. There are several ways of doing it, but one way is positive times orthogonal, and then by spectral theorem, positive matrix is orthogonal 1, P orthogonal 1 transpose times the other orthogonal, and then you get KAK decomposition. Well, the positive so becomes diagonal now, and that's it. And certainly, yes, determinant is 1 for everyone. So if you started with determinant 1, so it's polar decomposition or whatever. And there are other ways of proving, I think. But anyway, it's just linear algebra, so it shouldn't be surprising. But this is a very powerful thing, because then I take my sequence Gn and I write it as Kn, An, Hn. Hn is not a good guy. Let's call them Kn bar. Let's maybe conjugate Kn primes. Anyway, so just two compact guys. And we could take subsequences and argue with subsequences later, and I'm going to do it, but the best way not to having to insist in a lot of things is arguing by contradiction. It's not really necessary, so we could argue with slightly different way, but it's, I think in this case it's epsilon simpler to argue by contradiction. So after we have this KK decomposition, we say the following. So assume a contradiction Howe-Moore is not true, then let epsilon be positive and B, W, and G and I be such that by G and I B dot W stays larger than epsilon. I can even assume they are okay, these are complex. If we are real, I can certainly assume this. If they are complex, I can also do that, but okay, let's just put the absolute value. So the modulus here. And this is for every Ni, and then we do the typical trick of forget about the Ni. So let's just assume that this is true for the sequence Gn. And the same will be true for any subsequence. So now I write this sequence Gn as Kn, An, Kn prime by the Knk decomposition. And since the Kn and Kn prime belongs to the compact, by taking a subsequence, which I'm not going to take, you can take Kn going to K and Kn prime going to some limit K prime. So you have these limiting guys. Okay, so we have all this business there. So we obtain that pi kn, actually let's do it, so pi an times pi kn prime times v dot pi kn inverse or transpose of w is always larger than epsilon. Okay, on the other hand, I have that pi of kn prime v goes to pi k prime v, and in the strong form, and pi kn inverse w goes to pi, okay, yes, inverse w in the strong form. And by giving up the epsilon and again taking not even a subsequence, starting the sequence later, this will imply, since this happened in the strong form, so in the norm form, this conversion, this implies that pi an times this guy I happen to coin. So this is v bar, and this is w bar for every n. For every n large enough, but for every n. Okay, this is just some very, it's even simpler than before. You compare this with this guy, and this, the difference between this and this goes to 0, so it has to be larger than epsilon over 2. Well, actually, since it's strict inequality, it's larger than epsilon, so we are good. Okay, so now we started with the Gn, we took subsequences, did a lot of reduction, we end up with similar contradiction, similar problem, but now an are diagonal with positive entries. So e to the t1 n, and I typically call it tn, but now dimension is d. Okay, so we are not in SLN. Okay, let's, because I'm always in SLN, so let's call it AK, and then it's still SLN. If not, I should switch to SLD. Okay, and now we saw who are the guys playing the H form. Okay, so we take this type of H, which has some non-trivial entry in the ij direction, and the rest is 0. And these guys typically will go to the identity if I do the conjugation, if it is chosen in the right form. Okay, so I do a k h I j, and actually let me put a, let's put the ij up above. Let's put the subscript s. So we wanted the inverse here for Mautner, and this becomes h, and we said that this is t I k minus, oops, e to the, wait a second, yes, e to the t I k minus t j k times s. Could be this or minus that. The minus this, no? Yes, because I put the inverse here and not here. Okay, so we have this. So as long as tik minus tjk goes to plus infinity, we are good. So this will do the subs. Okay, now the sequence ak is given to us. We cannot change it much, so it's just given to us. So that's one important observation. A second important observation is, since these guys are compact and actually are convergent, the fact that this guy goes to infinity implies that this guy goes to infinity. So this can be easily seen with the norm, but also from the escaping from every compact, it can be seen as well. Which means that the entries here have to, at least one of them have to go to infinity. And since the determinant is 1, so the sum of the TI's is 0, it means that at least one of these difference has to go to infinity, plus or minus infinity. Moreover, we can even take a subsequence if we want and look at the asymptotics of these guys. So we have this T1. I'm not going to do it because I'm going to do something epsilon different, but we could do the following. So you take T1, T2, Tn, k, divided by the norm of this guy, so the maximum of this, doesn't matter who it is. And this goes to some vector b, which tells me that these vectors are approaching some direction. And then I can make this discussion according to who is this b1, bn, and I can look whether b1, so whether this is 0, positive, or negative. So it's a norm 1 vector, the vector of these guys, and the sum of the entries is 0 because this is what happened for each of the guys. And then I have the ij's where this is positive, and then I have to discuss whether the denominator is going to infinity. So if bi minus bj is positive, then I have this is good. If bi minus bj is negative, then bj minus bi is positive, and then I just take the guy, which is the other direction, and these are the good guys. Yes. Yeah, that's the unitary vectors in this direction of the TI, and then it approaches this direction. It's just for the finiteness. I have to take some subsequence in order that this is convergent, and then I know that this guy is going to infinity into this direction, and so that's, again, I could do it, but at the end of the day, the only thing, since this vector, well, I will know a little bit better than just trying to argue minimalistic, which is I have a lot of ij's with bi minus bj positive. So it's not just one, because if only one of bi minus bj are positive, then all the others have to be equal, but once the others are equal, then you do bi minus bj prime. So if you have this, then when you do bi minus bj prime, is also positive, because, and that's the way you get a lot of I and j. But this is a discussion that will come later, okay? Because we want to use Mautner now. So what does Mautner tell us? Mautner tells us that pi, okay, before Mautner, we take z equals to the weak limit, again, taking subsequence of pi in v bar, and Mautner says that for every ij such that Tn, so this Tik minus Tjk goes to infinity, I have that pi 8ij of z equals to z. Very good. And now comes why I was saying that I'm coming minimalistic, because the typical argument here, one could really argue directly on SLN, but I'm following what everybody does, which I think is very smart and is also useful not to get lost in the middle of the arguments, especially when you are in even larger groups, because SLN more or less is easy to handle, but for the larger, really you want to do something simple, and what is simple is to play with SL2, and that's what people do always in representation theory for simply group and semi-simply group. You go always to SL2 and understand SL2, because SL2 is the building block for all simply groups and is the building block for the representation theory as well. So what is the SL2 that we will care from this picture, and then we move to SL2. So we have this entry, actually the following entry, which is this S here, all ones down there. And then this entry comes inside an SL2, which is put e to the t, e to the minus t here. Well, actually it's not e to the t, you put whatever b w here, and the rest is 0. And bw minus as equals to 1. And all these matrices of this form is a copy, which sometimes is denoted as Ij, a copy of SL2 inside there. And then we look at this copy of SL2. We restrict our representation pi to this copy of SL2, and we notice, so we already applied Mautner to the whole theory, and we won this invariance. So when I restrict to this copy, I get that pi this entry. So let me do the identification now. This BSAW with BSAW here. And then through this identification, I get this fact for ABS. So for this SL2R representation, this upper guy has this invariant vector. And now comes the second sort of ergodicity statement, which is different from Mautner in philosophy, and the proof is different. The fact that this guy is invariant by this unipotent implies that this guy is invariant also for the diagonal, and also will be invariant for the other unipotent. And then once it's invariant for everyone, it's invariant for this SIG, which implies that I got invariant for this guy, then I got invariant for this guy, which has all ones, and I also have invariant by this A. Then you see how much invariance I got. So let's prove that. So this is lemma. Is pi e to the t e to the minus t. Okay, let me just write it completely abstractly, since it will be simpler than keeping the notation. So let pi be representation. Now I am allowed to have invariant vectors, even though I could always do it, the trick of taking the perpendicular, but doesn't matter for this proof. The typical continuity pi gn x minus x goes to 0 when gn goes to identity. And assume pi of h z equals to z, where h is actually only one s would be enough, but let's do it for just invariance by the whole flow. Then this z equals to z for everything. I could do directly state invariance by the whole SL2R, but that's how the proof goes. So you do it in 2 steps. So we do it in 2 steps. Now the proof is really beautiful. I don't know who had first this idea. Probably go back to Cartan or maybe before Cartan. So it's quite an old type of game. Maybe it's after Cartan, but it's certainly beautiful. So okay, so how you do it? You define your function f of g as being pi h of c, pi g dot z. Let me see if that's exactly how you define it. Okay, yes, of course. My bad. I shouldn't need to do that. Okay, yeah, we have this. Okay, so what's the property of this guy? The property of this guy is, so we have this group H, which is generated by little h. C could be 0. It's good for us. Because if z is 0, then the thesis is trivial. Actually, it will have to be 0 at the end of the day. So, because the way we got the C and the proof the way it goes, z has to be 0. If we believe Howe-Moore is true, when we take that limit, it has to be 0. Of course, we are in the middle of a contradiction. So we could assume C is not 0 for that matter. But again, as I said, so the fact of taking the epsilon and making the contradiction is so that whenever I take a subsequence, I'm not really losing information. It's just the only reason. If not, I could just argue all the time. I take subsequences and I keep on taking subsequences, and I argue with this limit, and I prove this limit is 0 for this subsequence. And then I should argue that if for every subsequence the limit is 0, then the limit is actually 0, which is also true. Okay, but instead of doing that, I just choose the epsilon. Okay, so we have H is this group, 1, 1, 0, H in R, and we get that F S in R of G times H is pi G times pi H of Z dot Z, but C is H invariant, which means that I can forget about this guy, and this is F of G. So it's H invariant when I move to the right. Now when I move to the left, I have pretty much the same, because this is H pi g c dot c, but then these are unitary operators, so the pi h goes to the other side as pi h inverse of c, and against the h invariance tell me that this is c. This is also f of g. So this function f is both left and right invariant, which is a very good news. Oops, sorry. Now with this I would almost been done, essentially. I don't know. It's really beautiful what they do next. One could do it differently if you want. What I mean with doing differently, so I have f of g, and then I'm allowed to multiply on the left by h1 and on the left by h2, and this is always f of g. And the question is how much I could multiply. And, well, this requires some discussion, which one could do it through linear algebra mostly, to play a little bit. They do it more symmetrically, which is still some sort of linear algebra. Okay, so how far you can do. But I need one more observation, which is this function f of g is a continuous function. Okay, and this is because of the strong continuity of this guy. And here is really the beauty. So I can consider the quotient g mod h, which is not a compact quotient. It's a two-dimensional quotient because SL2 is a three-dimensional space, h is one-dimensional, this is two-dimensional. And certainly f defines a good function, complex, real, doesn't matter, by f of g times h equals to, and this is well defined. And then I have the h action from the left still on this guy. And I could do the other quotient, but that's the game, you don't want to do it. And the reason for that is you want really to see the picture. So what is g mod h? So g mod h is R2 minus the origin. And the way you identify it with R2 minus the origin is similar than what we have done before. So you look at G acting on R2 in the obvious way. A maps to A times B, or A comma B maps to A times B. So that's the natural action of A there. And you take one vector, which I guess is this one, the one we want to take, and you look at the stabilizer of this vector. And the stabilizer of this vector is H. So because A of 1, 0 equals to 1, 0 is exactly the fact that the matrix is 1, 0, H, determinant is 1, so you need to have a 1 here. And this implies that I can identify the orbit of this vector 1, 0 with G mod H, and it's multiplied to the right because the invariance comes from the fact that I put the H here and I apply it to the B and I get the same B. Now, what is the orbit of 1, 0? So the orbit of 1, 0 is all non-zero vector, because by an SL2R matrix, any non-zero vector can be mapped into 1, 0. And that's why you get R2 minus 0. And now we get the left action of H on this R2 guy. So how does this H act when I'm identifying this with G mod H? Okay, and the claim is that this action is essentially the standard action of H on R2. And this actually should follow from this quotient and just what is in there. So once we have this, so this is standard action on R2, and now finally comes the picture. I have 0 here. Now I take a vector here. When I multiply this vector by this matrix, since it is in the positive, it moves this direction. When I multiply in the bottom, it goes this direction, and these guys don't move at all. So I have f of h1 g times h is for every h1 and g on one hand, and actually directly write it this way, just because this is a vector. And on the other hand, I have then that f is constant along this line. So if G1H and G2H both belongs, actually it's constant on horizontals. Yeah, maybe let's write it this way. So f is constant on horizontals. I guess that's much simpler explanation. So the fact that it's constant on this horizontal is because the H acts transitively on this horizontal. The fact that it's constant on these other horizontals as well, the only non-trivial is the horizontal through 0, because there you don't act transitively, but here you use continuity. And being constant on horizontals is a continuous matter, so it goes to the closure. Which means that f is constant on all horizontals. Okay. Actually, this should do it, but now I don't remember how you kill it once you get this constant in the all horizontals. So why this solves all our issues? M? F is constant. Well, no, because the value could change from here to there. Okay? So we have to, so it's not constant everywhere, but that's okay that it's not to be constant everywhere. So what are these guys? What are these vectors here? So these vectors here are exactly the diagonal vectors. Okay, the vectors coming from e to the t, e to the minus t, 0, s applying to 1, 0. So these are these vectors here. Okay, so hence what I get is that is constant. So the little f is constant for this guy. So no matter what is the value of t, s, and minus t, little f is constant on here. Okay, so that's what we got. Let's write it down. So this continuity allows us to tell that f of e to the t s0 e to the minus t is equals to f of identity, because it's one special case of this, times, oops, for every t and s. That's what we got. Now, this, we will keep on working with f later, but let's finish this lemma first. So what does it tell us then? It tells us that pi of g z times z is equal to c times z for every g of this form. And actually, we don't care about the s because we knew invariant for this s, so this is really the important guy. But now it's Cauchy-Schwarz, because this is norm of z squared, and then this is, if you want, I put absolute value less than norm of pi g of z. Oops. Which is equal to this, because things are unitary. And Cauchy-Schwarz tells me something when you have equality. Cauchy-Schwarz tells me that these are equal. Modulo of lambda has to be 1, because they have the same norm. And you have to do epsilon else to kill this lambda. How do we kill this lambda? If things were real, it's very easy, you see? Because if everything was real, then lambda is either 1 or minus 1, and you cannot do minus 1 by continuity, because you cannot jump from 1 to minus 1. But here is complex valued, so how do I get rid of the complex number? Oh, because I still know this. So I have equality without the absolute value here. So it means that lambda z times c equals to c times c, which means that lambda equals to 1. Unless c equals to 0, but if c equals to 0, there is no discussion here. Okay, so that gives us this game. And now what's next? Once I have invariance by the upper triangular matrix, I just go and do exactly the same, but instead of with H, with the group of upper triangular matrices. We're out of time. How much? Okay, I need 2 minutes. So, because with this we finish the SL2 version of Howe-Moore after all, and then on Monday we can just do the trick for SLN and do probably some property T, and we are good. Okay, now the next lemma says that we have P is this group, T in R is in R, is the group of upper triangular matrices, and we have as before, so pi from SL to R, unitary of H, and same continuity as before, and we assume pi of P Z for every P in P, then pi of G for every G. And we have an invariant vector. So the proof essentially continues with the same f as before, but now, and the bottom line will be the same as before. Once it is constant, it's pi of c equals to z. So but now f goes from G mod P because I can quotient by P. And I can that f of G equals to this, and we know that f of P times GP now it's better is equals to for every P and G. We have the invariance to the other direction. And then essentially we are done because we know by the same discussion as before, so P is the stabilizer of all these guys. G mod P is actually the circle. And we know that the P action has essentially two orbits. One orbit which is the direction 0, 1, and the other orbit which is the rest of the circle. And or the other way around. One orbit is the 1, 0, and the other is the rest of the circle. Well, anyway, doesn't matter. So there are just two orbits. One orbit is a point, the other orbit is the rest of the circle. And the invariance by P tells you that the function is constant on the complement of a point, but this is a continuous function, so it has to be constant. So this implies f is constant. And we are done. So then we do the same trick as before. So these are really great picture of what's going on in the spectral theory, in a sense of the group action, and the representation theory. And I think it's very nice because it gives you a different perspective on how to prove ergodicity. So the typical way we would prove these things in dynamics wouldn't be along this type of argument. So you would do some ergodicity first, while here we are trying to prove mixing. So we would have first some ergodicity, and then the mixing will come from, again, the unstable directions and nice distribution of unstable directions on the picture, which are true here, but you don't see it explicitly here. So here you just go to the representation theory, play a little bit with these guys, and of course the density of unstables comes from this fact. So you should think this as being the center unstable foliation. So in this SL2, you have that this is the dynamics, this is, say, the stable foliation and unstable, depending on which direction you are going. And in the first argument, there was an argument that when you are invariant by the unstable, you also are invariant by the diagonal dynamics, which is the hyperbolic dynamics. But once you have invariant by the hyperbolic dynamics and the unstable, then the unstable becomes this, which is the P, which is dense. And here density is very clear, it's a complement of a point. The fact that it's a minimal foliation on the space and the conditional measures are nicely distributed is much harder to prove conceptually. And when you do this approach, it's just become this circle becoming dense when you take the complement of a point. And that's all the argument. So it's really much simpler. Okay, so we finish the SL2R of Howe-Moore, and then we are going to start embedding SL2Rs into SLNR until we get full invariance by SLNR. And that's essentially how the game goes. Okay, I guess that's it. It's too late. Thank you.